Welcome to Module 2. This module is designed as an introduction to data hiding. What specifically is data hiding? The term was coined for placing data in a directory which is apparently inaccessible for the normal user. The data is not protected by any other attack prevention method. The only security offered by data hiding is its apparent obscurity. The exact location of the data is unknown. What could go wrong? As we can easily imagine, data hiding is far from safe. Anyone who discovers the directories, either intentionally or by accident, may access hidden confidential data. We may compare data hiding to burying a treasure in your backyard. If someone knows the treasure is there, or discovers it purely by accident, they may dig it up and take it. The same may be said of web applications. If we hide data in this way, and by hiding, we simply mean the links aren't viewable or published, the information is still not safe. Data hiding is very often used in conjunction with the robots.txt file. The robots protocol prevents web robots used by search engines from accidentally indexing or categorizing data we'd like them to ignore. Here's what the file could look like. As we can see, the file contains instructions specifying which directories and their contents should be ignored by web crawlers. Unfortunately, the file is quite often used to describe locations containing confidential website data. Many website developers believe that storing such data in robots.txt will prevent them from being leaked by accident. Robots.txt is purely informative, relying on bots to cooperate and honor the instruction to not index specified directories. It is, however, not taken into account by web servers. Additionally, as you can see, any user may access the robots file. If we put confidential information, such as data location, in robots.txt, we practically invite an attacker to try and steal them. The example shows two specified paths, which should not be accessed by web robots. The directories admin and data. A lot of potentially interesting data may be stored there. Let's see what's inside. As we can see, after we have typed in the path, a page opens. We may browse it freely. This is the essence of the data hiding process. The method doesn't give you a link to the page, but if its location becomes known, it may be accessed without trouble. It's the same for the other directory. After you type in the path, you may access all data, which in theory should remain restricted. Although this scenario may seem a bit abstract, web developers often use it purely because it is convenient for end users. If you follow news from the security branch, you may have heard, even lately, of websites which have protected critical data through the data hiding method. This has led to major leakings. Applicants' resumes being leaked from job search sites is an example of problems connected with data hiding. Another example is the American Express website, which left the access to application developers' administration panel unprotected. By and large, data hiding is not a safe attack prevention method. Remember that confidential data must be secured with an authorization scheme. Don't simply rely on robots.txt. The file does not give you a lot of security and may just become the hole through which an attacker slips in. This is all for now. Thank you for your attention and see you in Module 3, which will talk about how web applications may be affected by brute force and dictionary attacks. Welcome to Module 3. This module focuses on brute force and dictionary attacks. These types of attacks are the easiest form of targeting web applications. They consist of checking all possible rule-based or dictionary combinations of logins and passwords. Cracking the password may not take a lot of time, so in practice, these types of attacks are often unsuccessful. The HTTP auth scheme is the first authorization method that may be exploited for attack. It is implemented in all web browsers, and virtually all web servers enable setting it in an easy way. Here, we'll talk of HTTP auth implemented in the Apache web server. The core of this scheme is htaccess, a file used for many purposes, including HTTP authorization. If you store it in a directory accessed by a web server, all the files contained in the directory will become protected with the user ID and password. You may specify the message which will be seen by users and indicate the file containing passwords used for authorization. Let's now try to create such a file. In Apache, the command htpasswd is used for this purpose. Here you may see the syntax for calling the command. To create a file containing passwords, you must first enter the name of the target file. It's good to mention that files with the extension htpasswd and htaccess are protected by the web server by default and may not be accessed by users. Regardless of this, it's better to put files outside the document tree of the web server. Next, we enter the username and password. Our password here is 1234. The file has been created. Now let's see how this works in practice. We'll use the Live HTTP Headers add-on. The extension allows us to view the live communication between browser and server. As we can see, the web server has a set special header, www authenticate, instructing the browser to authorize the user. First, we'll enter an incorrect password. As we can see, the browser encodes the login and password with a base 64 scheme, and a special HTTP header is set. The server decodes the string and compares it against data stored in htaccess. Let's now submit the correct login and password. As we can see, this time the authorization is successful. Browsers remember requests for authorization and the provided data. The information is transported automatically with each attempt to access protected resources. Because of this, no further authorization will be needed. Let's now try to launch an attack targeted at this authorization scheme. To do this, we'll use Hydra, an application that enables dictionary attacking a variety of utilities, including the HTTP auth scheme and web forms. We can see here the description of parameters of calling Hydra. For the parameter L, let's submit the file containing a list of usernames. Let's see what these dictionaries look like. They are simply a list of words which may constitute usernames or possible passwords. We can also see that the files include our login and password. Next, we submit the file containing the passwords dictionary. We also need to submit the address of the web server which will be analyzed and the name of the attack. Next, as a method parameter, we submit the path to resources which require such authorization. Let's now try to start the command. As we can see, the sample attack has been successful. One service has been targeted, 21 login and password combinations, and also our access information have been found. It may be worth it to take note of another authorization scheme. It's a simple login form created in the PHP language. It is displayed by default. If a user submits the form to script, the provided data are compared against the data held by the corresponding variables. To log in, the user must type the username admin and the password root. Let's now see in practice how the scheme is working. Submitting incorrect login and password will cause the message error to be displayed. If the correct information is given, the message logged in may be seen. Now we'll find out how Hydra may be used to launch an experimental attack on the form. Indicate dictionaries which will be analyzed by the application. The dictionaries include the correct login and password to our script, so the attempt should be successful. Here, the server name must also be given. This method is called HTTP post form, as the form is passed via the post method. Method parameters are the form's address, data string, and the message displayed with each failed login attempt. Provide the string representing the encoded form after the colon. The value user is changed to logins selected by the application. While pass is similarly changed to checked passwords. We also need to pass the field, Go field, which is used for logging in. Enter the message displayed with the failed login attempt after the second colon. Let's see how this command will work. As we can see, the attack has been successful. The login and password combination has been found. The demonstrated examples used ready-made dictionaries. Let's think what could be done if we didn't have access to such lists, or if for some reason they remain ineffective. The solution is John the Ripper, a password cracker which also enables the generating of password strings for brute force types of attacks. The John MMX version is faster as it utilizes special processor instructions. While it may be quite aged, the application is still fully functional. As we can see, the command may be executed in different modes. We're interested in the incremental mode, which generates character and digit strings. This may prove useful in brute force types of attacks. The incremental mode assumes the parameter mode, which defines character sets used to generate new passwords. Let's start with the standard set digits. You must add the parameter stdout to write the generated passwords to standard output. Alphanumeric characters is the second mode. Another is all, a mode for generating passwords from all characters. Generated passwords are passed to a standard output, although they may be redirected to a file to generate a dictionary. The dictionary may in turn be used as a parameter of calling Hydra. As we can see, the file has been created. So how can we protect ourselves against these threats? The first and most significant solution is to force users to use strong passwords. The stronger the password, the more time a brute force attacker will need to check all possible combinations of characters. Passwords should not use words listed in popular dictionaries. It may often be worthwhile to introduce a scheme for blocking a user session after a limit of failed login attempts is reached. We must remember, however, not to provoke an account lockout, a situation which occurs when users are locked out of their accounts. We'll talk more about this in the next module. That's all for now. Thanks for your attention, and see you in the next module. Welcome to Module 4 of our course. This module will focus on account lockout vulnerability. We'll start with helping you understand the core of this concept. We may talk of an account lockout vulnerability if an authorizing script which monitors the number of login attempts is set to lock user accounts after a limit of failed logins has been reached. If an account is blocked without blocking the IP address used for attempted logins, a potential attacker who has obtained the username and attempts to log into its corresponding account, may exploit this by blocking the account of a normal user. The attack results in a denial of service and may cause users additional problems. This authorization mechanism is frequently implemented in online banking. If a user submits a valid username but enters an invalid password for 3 consecutive attempts, the account is locked. To unblock it, the user has to contact a branch or call a helpline. The procedure could be helpful in preventing attacks, as the potential attacker has only 3 guesses at the correct password for the targeted username. On the other hand, anyone who has acquired our username may use it to successfully deny us of our own bank accounts. Take a look at the example of how this mechanism works. We can see here a simple website created in PHP. The site employs a simple database-based login mechanism. As we can see, a PHP session mechanism is being utilized here. We're connecting to a database. Let's see if the session has successfully started. If it has, load information from the database on whether the account is locked. If it is, simply stop the execution of the script. Here's the part responsible for logging users out. It deletes the session variable, which identifies users. If the session is correct, a displayed message notifies users that they are logged in and may log out. If the session fails, a login form will be displayed. After sending the form, we may load data on the user who is matched to the given login. If we manage to obtain the information, it is processed further. But more on this later. If we're not successful, an error message appears. Now back to finding a user who holds the specified login. If the account is locked, we disable the login option and display a message stating the account is blocked. If the data is valid, declare a PHP session and display the link in the main page. If the provided password doesn't correspond with the password stored in the database, we first display an error message and then check the number of login attempts. First, the field will hold 0. The value will increase with each failed login attempt. If it becomes equal or greater than 2, this means that at least 3 failed attempts have been made. We display an appropriate message and block the account in the database, denying the user access to the account. If the limit of login attempts has not been reached, simply increase the count in the database. As we can see, IP address and special cookies are not checked here, which means that the account will be locked without regard to the computer used for login attempts. Let's see now how the service works in practice. For the purpose of this example, a user admin has been added to the database. The password is test. Let's try to log in using these credentials. We've logged in successfully. We may now return to the main page and log out. As you can see, the mechanism is working correctly. Log in again. Refreshing the page will display a message stating the user is logged in successfully. But let's see what a potential hacker could do with this situation. switch to the private browsing mode. New cookies will be collected, and so a new PHP session will start. The user is not logged in for this session. The page opens and, as we've predicted, we're no longer logged in. Let's try to imagine how an attacker could exploit this situation. The attacker knows the admin account has been created in this service, either because he made a correct guess or because he acquires this information in some manner. Now submit an invalid password. The message displayed, unsurprisingly, states that the password is incorrect. Let's do this again. After the third failed login attempt, the message states that the account is blocked and the user must contact an administrator. This means that the attacker won't be able to try new passwords. The same message will display each subsequent login attempt. Let's see if this will happen. As we can see, the account is locked. Let's find out how this affects a user who is already logged into a service. Switch off Firefox's private browsing. We're back in the previous session. As you can see, the account has been locked. The session exists in the system, but the database stores information that the user is blocked. We can see that this mechanism could be a source of problems for normal users. A potential attacker could block a user account knowing only the login, and this information is frequently explicitly displayed on websites. All it takes to block a user is to submit several incorrect passwords. If this mechanism is implemented, for example, in an online auction service, an attacker could temporarily prevent the user from bidding in an auction. How can we prevent this attack? Blocking the computer used for failed login attempts is a better alternative to locking users out of accounts. This could be achieved, for example, by tracking and banning an attacking computer's IP address. There's little chance of the attacker and targeted user sharing the same IP address, and on the upside, this approach prevents normal users from experiencing problems, while we're still able to thwart brute force attacks on our service. That's all in Module 4. Thanks for your attention. The next module will focus on web parameter tampering. See you there!